Let's talk about the general procedure for solving intersection problems. So the first thing about an intersection problem is that an intersection is when the objects are at the same position at the same time. And so what that means is the way that we solve them is that we want to find out an equation for position as a function of time for each object, right? So we're going to go ahead and find an equation for each of them, and then we're going to use those two equations for position and set those two positions equal to each other, and then we can find the time when they intersect. And that's the general idea of what we're trying to do. And so you're like, well, how do you go about finding those equations for position as a function of time? And so the key thing about that, we say, intersection problems are kind of crossing a line to a little bit more complicated sort of situation where our first step is always going to be to make a sketch. So we're going to make a sketch of the situation showing the two objects, showing them how they're going to move. And on the sketch, make sure that you include arrows, include vectors to represent any velocities, accelerations, and displacements. All three of these things, right? They're vectors, they're arrows, they have directions to them, and we care very much about what those directions are, positive or negative. We're going to use the sketch to help us figure these things out. Once I've drawn my sketch, then I'm going to drop in a coordinate axis, a position axis, and then I'm going to choose where the zero position is on that axis, and then mark any other known positions. Now, once I've done that, the coordinate axis is what sets the directions. So I'll have to go back and double check and fix the signs on any of those velocities, accelerations, and displacements. Now that I've dropped the coordinate axis in and I've decided which way is positive, which way is negative. So I got to go back and double check all those values and make sure they're right. Okay. Once I've done that, then I have the information I need to make my position as a function of time equations for the two objects. So we're going to write those positions as functions of time. And when we do that, we now right now we have two equations for this course that have position as a function of time. The first one we figured out in the constant velocity unit. So that's x equals vt plus x naught. This equation is only good for objects that have a constant velocity. Because you remember, we got this from a graph of like the slow buggy moving, or slow or fast buggies moving. And when they're moving, they moved at a constant velocity, and so their position time graphs were straight, they were linear, and that let us write y equals mx plus b for the position time graph. And that's how we got that equation. On the other hand, if it doesn't have a constant velocity, you cannot use this model. And so we model it instead. For something that has a constant acceleration, we can use this equation that we developed from the cart rolling down the ramp lab, the accelerated motion lab. We got this delta x equals v naught t plus 1/2 at squared equation. But remember, our goal is to find position as a function of time. So position as a function of time, like, well, here's time. Well, the position is wrapped up here in this delta x. So remember that delta x, you're going to want to substitute in, for where it says delta x, you're going to want to substitute in a x minus x naught, right? And then I can move the x naught to the other side and I'll have an equation for position as a function of time. So that's the trick there. So that's once I have these two equations, my position is a function of time, then I can set those positions equal to each other and solve for the time when they intersect, and then use that information for whatever else they want me to solve for. Okay, so let's check this using a sample problem, right? Let's go ahead and try this procedure. So for my sample problem, I went ahead and wrote this one. So say that we have this sick gazelle, and the gazelle doesn't hear this cheetah sneaking up on it till the cheetah is only 30 meters away, running at 8 meters per second. The gazelle's ears perk up, and the cheetah spots this. The gazelle begins running away from the cheetah, accelerating at 4.2 meters per second squared. The cheetah then accelerates after its prey with an amazing 8.9 meters per second squared of acceleration. How far does the gazelle run before it's caught by the cheetah? So you're like, well, I got two moving objects. Looks like they're both accelerating. It's a complicated sort of thing. Let's start off by making our sketch. So for my sketch then, again, I'm going to draw in the cheetah and the gazelle. All right. So my gazelle, we'll say, maybe the gazelle starts off here, right? Right? And you say, hey, that gazelle, it's gonna start running. So it's gonna start with an initial velocity of 0. And when it runs, it's gonna have an acceleration. It's gonna start running away from the cheetah. So it's gonna start moving to the right here in this picture. It starts moving that way. It's going to have an acceleration to the right of 4.2 meters per second squared. Okay, now the cheetah starts off 30 meters away. So cheetah, I don't know, what's a cheetah look like? Yeah, I've never tried drawing a cheetah before in my life. Oh, there we go. Give it a kind of cattier. There we go. All right, that'll work. Okay, so the cheetah, on the other hand, let's use a darker color for that. So first of all, it starts off 30 meters away. And the cheetah is running at 8 meters per second to start with. So I've got my vector. It's run after the gazelle. Its initial velocity is 8 meters per second there to the right. And it has an 8.9 meter per second squared acceleration. Now it's getting faster, presumably here. And so if it's getting faster, that means the directions of the velocity and acceleration have to be the same. They've got to be in the same direction. So the acceleration has got to also be to the right. And that's got to be this 8.9 meters per second squared. All right. If your velocity and acceleration are against each other, opposite directions, that's when you get slower. All right, so we got that. So now you say, all right, what else here? At this point, you might consider dropping in your coordinate axis. Again, I'm thinking about the gazelle's going to be running away from the cheetah, and the cheetah's going to be chasing it down. So we're going to be moving along this axis. So here is my position axis. I've got to choose somewhere to call 0. I'm going to choose to call where the cheetah starts here. Let's call this be x equals 0. Well, if this is x is 0 and the gazelle starts 30 meters away, this must be x equals 30. And as soon as I set that as x equals 30, look, now I've got position 0, I've got position 30, then I must be adding to get to 30, right? To the right is now officially the positive direction. So as soon as I drop that coordinate axis in and set some positions, that now sets this so that to the right is positive. So at this point now, I need to go back in and double check the signs on everything. This velocity is to the right. That's the positive direction, so that should be positive. Acceleration's to the right. Right is positive, that should be positive. The gazelle's getting faster, accelerating to the right. Again, positive. Everything here is positive. That's all good. There's actually one more thing that I might want to sketch on this. The other thing I might want to sketch here is my displacements. So we're figuring this cheetah is going to catch up to the gazelle somewhere. Let's say that here is that magical spot where we catch up. Then the gazelle starts here and goes this way. That's the displacement for the gazelle. On the other hand, the cheetah is going to start back here. and it's going to catch the gazelle there. So dot, 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 dot. That whole thing, that's the displacement for the cheetah. Okay, to get to that line. Okay, so there is a way of solving this using the VT graphs also. I'm going to come back and show that, and we'll use these displacements to help us solve that. But for now, let's just move on with using the mathematical model technique. Okay, using the equations for position as a function of time. We'll use that one first, and we'll come back and I'll show you using the VT graph. Okay, so continuing on. So I've got my information down. I'm ready to go ahead and start modeling these two motions, the gazelle going from here to here, and the cheetah going from here to here in that same time. So I want to write my position as a function of time equations. Again, both these are accelerating, so they do not have constant velocity, so I cannot use x equals vt plus x naught. That is for constant velocity only. I'm going to end up using this formula. Again, this formula came from the cart rolling down the ramp. We got it from actually looking at the area under that diagonal velocity time graph is actually where this equation came from. And so if it was a diagonal velocity time graph with a straight diagonal line, and the slope of a velocity time graph is the acceleration, constant slope, then it had to be a constant acceleration. So that is the limitation on this formula. It's only for constant accelerations. Let's go ahead and apply it for both of them. So what I would do, take a look at my sketch, I would write my position as a function of time equations for each. I'm going to do this on a separate sheet of paper here. So if I go to write position as a function of time for the cheetah, then that equation is going to look like this. Let's do the cheetah in orange. So again, I always write the formula before I start plugging anything in. The base formula looks like this: delta x equals v naught t plus 1/2 at squared. If nothing else, it'll help me memorize the formulas. You say, hey, I'm trying to solve for, now the thing you gotta be careful about is we're trying to solve not for delta x, we want the position x. So I'm gonna substitute in x minus x naught. Okay, and then I would move that x naught to the other side. However, in this case, what is the starting position of the cheetah? Oh, we set that to be 0. So that x naught is actually going to drop out nicely for us. The starting velocity, so let's, I'm going to go ahead and I'm going to copy down with the values in that we know. So because that x naught drops after that, the starting velocity for the cheetah was 8 meters per second. Now, again, I want to leave time as a variable. And the acceleration of the cheetah is 8.9. So what I have now is an equation that has two variables, position and time. And so what that means is I can substitute in for t any time and find out where the cheetah is. In fact, I'm going to put a subscript c on this so I know it's the position of the cheetah. So I can find out where the cheetah is at any time. That's what this lets me do. I've modeled the motion of the cheetah now. I've got a formula that represents it. I'm going to do the same thing now for the gazelle. We'll do the gazelle in brown. So for the gazelle, so we're going to use again that same formula, delta x equals v naught t plus 1/2 at squared. We say that again where it says delta x, I'm going to sub in x minus x naught because I really want an equation for position. Add that x naught over, so it's going to be position of the gazelle. Okay, that x naught, I'm going to move that x naught to the other side. So what's the starting position of the gazelle? Well, the gazelle started at the 30-meter mark. The starting velocity for the gazelle, it started from rest, so that whole v naught t term is just going to drop off. So then I just have that 1/2 the acceleration of the gazelle t squared. And so here I have an equation for position of the gazelle as a function of time. I can plug in any time, find out where the gazelle is, or plug in a position, find out what time they're there. So that gets me now my two mathematical models. And my whole goal here, again, we're doing an intersection problem. And the whole point of an intersection is that the intersection is when the objects are at the same position at the same time. So what I want to do is I want to set those positions equal to each other to find the time when the positions are the same. So I want to set the position of the cheetah, I want to set that equal to the position for the gazelle. Well, the position of the cheetah is equal to this. So I could write 8t plus half of 8.9, 4.45. Okay, and that's got to be equal to, on the other side, the gazelle's position equation. 30 plus half of 4.2 is 2.1, right? So these, there will be, so what I'm doing here is I'm saying the positions are equal. This is going to give me the times that go with when the position is equal. So I'll find the times when they're at the same position. So I need to go ahead and solve this equation for t. But you notice that I've got like some to the second power terms and first power terms and constant terms. So this is going to be a quadratic. When I rearrange this equation, let's see, I'll subtract the 2.1 t squared from the 4.45 t squared. That'll give me 2.35 t squared. And I have that 8t. When I subtract the 30 over to the other side, it'll look like this. Minus 30 equals 0. So there it is in ax squared plus bx plus c equals 0, the standard form for a quadratic. So now I can solve the quadratic using one of the techniques that we have for solving quadratics. Personally, I like to use the solver function in the calculator to solve my quadratics. So I do second. So on my TI calculator, I do second. Wait, I don't need to do second. I just want to go math. Sorry, math. And there's a whole bunch of kind of built-in little programs or apps here. At the very bottom of the list, there's solver. I'm going to use solver. It says equation solver wants me to put in the equation. So I've got 0 equals. I'm going to put in 2.35 and then use this x, t, theta, n variable button. I want that variable to the second power plus 8 times that variable minus 30. It already has the 0 equals there. Hit enter. It wants me to give a starting guess. I'm going to guess 3 seconds, and then I'm going to tell it to solve. So I want to do not enter. I want to use that solve, that green solve there. Okay. So to do that, I got to get alpha to get the green solve. It thinks about it, and then it gives me a number. It says, hey, 2.2555 seconds. So that is when the time. Wait, 2.255 seconds. That's a 2.555 seconds. Okay, but you might remember that quadratics have 2 roots. I mean, they could have a repeated root. This one doesn't. 2 roots. So I found one of the roots. I might guess the other one. So what I did was I gave it 3 as an initial guess, and it checked to see if 3 was an answer, and if it isn't, then it tries a little bigger, tries a little smaller, tries a little bigger, tries a little, and it keeps going until it hits a solution. So the solution that was closest to 3 was 2.2555, but there's a second solution to a quadratic. So it might be further away to the right, further, way bigger than 3, or it might be way less than 3. I think I'm probably going to get something way less. So let me try another starting guess. I'll make this one just negative 100 and tell it to try solving that, alpha solve. So it starts at negative 100 and goes and stops at negative 5.6598. So the other solution is to that quadratic is t is negative 5.6598 seconds. And you say, hey, which one do we want? Well, negative time, that would be before we even started. We don't want that negative one. So this is the root we want. So that's the time when the cheetah catches up to the gazelle. But what we want to know is not the time. We want to know how far the gazelle runs before it's caught by the cheetah. We're actually trying to find this displacement of the gazelle. So what I might do at this point, now that I know the time, is I would just take this time. This is the time when the cheetah catches up to the gazelle. I'm going to put that back into the gazelle's equation to find out where the gazelle was when it got caught. All right. And since I know the gazelle started at position 30, I can find out what this distance was. Okay, that displacement of the gazelle. So I'm going to take that 2.2555 seconds and put it back into the gazelle's equation here. Position for the gazelle, 30 plus 1/2, 4.2. T squared, well, where it says T, that's where I'm putting in this 2.2555 seconds, right? I'm just carrying a lot of extra digits here. I mean, I would round at the end for my final answer. Anyway, I can put in those values. When I solve this in my calculator, let's see here. It's going to tell me, it's here, 30 plus 2.1 times 2.2555 squared gives me a position of the gazelle of 40.68 meters. So that's where it was when it got caught. But I got to be careful. They don't want to know the position it got caught. They want to know how far it ran. The gazelle started at 30 meters. So they really want the displacement of the gazelle. Okay, which is going to be the final minus the initial. So that's going to be that 40.68 minus the 30. So the gazelle only ran 10.68 meters before it was caught. Okay, and that's it. So again, be real careful about what we want to set is we want to set the positions equal. So I had to make sure that I subbed in x minus x naught for the delta x's, and I set the x's equal. I moved the x naught over. But in this question, they want to know how far the gazelle ran, so then they did want the delta x for that. But I want to set positions equal when I'm solving for that time when they meet. And that's basically the procedure for solving using the mathematical models. Now let me show you solving this problem real quick using the graphs. So using the VT graph, right? Again, same idea. We're going to start off with our sketch and mark on the vectors we know, and mark in the displacements is key because there are two special things we know about velocity time graphs. One special thing that we know about velocity time graphs is we know that the slope of the graph is going to be the acceleration. But the other special thing that we know is that the area under the graph is the displacement. Now, let's see, the cheetah starts off running with a velocity of 8 meters per second. So it starts off here at 8, and then it's getting faster with an acceleration of 8.9. So that's a real steep line, right? Again, this is the cheetah. I know that the slope of that is the acceleration, which is 8.9 meters per second squared. Now let's draw in the gazelle. The gazelle starts from rest, so it's got a velocity of 0, and it has an acceleration of 4.2. That's smaller than the cheetah's acceleration, so I want it to have a smaller slope, a shallower slope. So maybe the gazelle's line looks like this. Okay. And then here is that magical time, right? That critical time when the gazelle gets caught by the cheetah, right? Now you say, hey, the special stuff we know that the area under the gazelle's VT graph, you say, hey, that's the displacement of the gazelle. And the area under, and that area in this case is a triangle because it starts from velocity of 0. On the other hand, the cheetah started off already moving at 8 at time 0. So its area, again, we always want to go all the way from the line to the time axis. And so that cheetah's displacement is not a triangle, it's actually a trapezoid. There is a triangle plus a rectangle. All right. Now I know this whole orange area is the displacement of the cheetah. So now I've drawn my sketches here, my VT graph, and I've got my sketch. And so the key thing is these areas are the displacements. What we need to do is we need to find a relationship between those displacements. That's how we solve using the VT graph. So solving with the velocity time graph. Again, same as before, we draw the sketch, drop in the position axis, yada, yada, yada. But we make sure that we label our displacements. And then we need to find a relationship between the displacements. So in this case, those lengths, those displacements, I can say, hey, look, it looks like the gazelle went this far and the cheetah went this far. And you say, but look, how far the cheetah went, that's 30 meters that they started apart plus the displacement of the gazelle. So that's the equation I can write here. I can say that that displacement of the cheetah you say, hey, that's equal to this 30 plus the displacement of the gazelle. I was not consistent with my color coding here. I apologize. Especially the cheetah is that 30 meters plus the displacement of the gazelle. I'm just going to use the color code I did on this graph. Okay. So again, this is not like one of our formulas for the course. It's just a relationship that we have to spot from the sketch. Okay, which again is another reason why that sketch is really important. Now that I have that, where it says delta x for cheetah, I can try to write an equation for that using the areas on the VT graph. That's how I'm going to get an expression for delta x cheetah and the area of the VT graph for the gazelle to get an expression for the displacement of the gazelle. So for the cheetah, that's going to be the complicated one because it's a trapezoid. I'm going to make it a rectangle plus triangle. You say, hey, what's the area of this rectangle? Well, it's got a height of 8. So hang on a second. So let's do this. The cheetah is going to be that rectangle plus that triangle. That's going to be equal to 30 plus the gazelle's triangle. Right? So if I run through this, you say, hey, that rectangle, it's base times height. So it's 8 times in that width there, that's TC. That's that critical time when they catch up. The triangle is going to be 1/2 base times height. The base of the triangle is that TC. You say, now what's the height? Well, the height here, that's how far I go up on the velocity axis. That's going to be this, which is the final velocity, right? Minus the starting velocity of 8. So I guess that final velocity minus this. So it's like v final minus the initial here. That's the rise on this graph, isn't it? Really, that's the height of that triangle. That's the rise. And you say, well, how am I going to get that rise? Well, I'm going to get it from the slope, from the idea that slope equals rise over run. So that slope So rearranging, I need to find the rise on this graph. So rearranging this, the rise would be the slope multiplied by the run. In this case, the rise is what? Well, the slope of the graph was 8.9. And the run, oh, that's just TC. So I can put 8.9 TC in where it says rise here. So I'm subbing in 8.9 TC. So that's going to be 8 TC plus half of 8.9 times TC squared. Okay. On the other side of the equation, I've got 30 plus the area of that brown triangle. You see the area of that triangle is going to be 1/2 base times height. The base of the triangle, that's TC. And the height of the triangle, well, that's the final velocity of the gazelle, right? That's what this value would be. The velocity of the gazelle when it gets caught. You see, how am I going to find that value? Well, that's, again, just the rise now for the gazelle's graph. So I'm going to say, well, how do I calculate the rise of the gazelle graph? Similarly, it's going to be slope times run. So for the gazelle's rise is going to be its slope, which we know, so I didn't write it on the graph, but we know, whoops, that slope is the acceleration of the gazelle, and the acceleration of the gazelle was 4.2 meters per second squared. So rise is slope times run, so it's going to be that 4.2, and the run for the gazelle is also TC. So I can put 4.2 TC in there for the rise. So that's going to make this 30 plus 1/2 4.2 TC squared. Okay, and this is giving me an equation now where there's only one variable. That variable is TC. That'll be the time it took to get to the point where they meet. Right? Okay. And you'll notice that this equation we got, 8TC plus half of 18.9 TC squared equals 30 plus half 4.2 TC squared. You say, hey, that equation, here's when we use the mathematical models, and we put these two models together, and you say, hey, this equation is this equation that we got there, right? Once I do the half the 8.9, I get 4.45, and half 4.2 gets me 2.1. So we got the same equation out using the areas on the VT graph. And so I'm going to solve through and get the answer the same way the rest of the way. So that's setting up using the VT graph. Again, you make the sketch, you label everything, and then you make sure you label in the different displacements, because you're going to use these to find the relationship between those lengths. That was this delta XC is 30 meters. This is 30 plus delta X gazelle. And then I could go ahead and then use those displacements, writing them as the areas of these geometric shapes, and setting it and writing it all in terms of this variable TC for that time, to the critical time when they meet, and then solving through for TC. So yeah, that's it. Okay, so that's generally the procedure for solving an intersection problem with accelerated motion. Hope that works for you.